Hi again, this is Dr. Joe Angley. In this presentation, we will be reviewing water quality, including the types of common contaminants that are present in water bodies, looking at the wastewater treatment systems and water regulations that have been successful in cleaning up waterways in the United States. After completing this lecture, you should be able to define the term water pollution and understand the most common sources of water contamination. We will also review the methods we use for sewage treatment and review sewage treatment and water quality in developing countries. Finally, we will look at regulations that we use to control water quality. Japan, Australia, and most of Western Europe have improved surface water quality in recent years. Sewage treatment in the wealthier countries of Europe generally equals or surpasses that in the United States. Sweden, for instance, shows 98% of its population with at least secondary sewage treatment, compared with 70% in the United States. And the other 2% have primary treatment. Poorer countries have much less to spend on sanitation. Spain serves only 18% of its population with even primary sewage treatment. In Ireland, it's only 11%, and in Greece, less than 1% of the people have even primary treatment. Most of the sewage, both domestic and industrial, is dumped directly into the ocean. The fall of the Iron Curtain in 1989 revealed appalling environmental conditions in much of the former Soviet Union and its satellite states in Eastern and Central Europe. The countries geographically and socially closest to Western Europe, the Czech Republic, Hungary, East Germany, Poland, have made massive investments and encouraging progress towards cleaning up environmental problems. Parts of Russia itself, however, along with former socialist states in the Balkans and Central Asia, remain some of the most polluted places on Earth. As we saw earlier in this chapter, at least 200 million Chinese live in areas without sufficient fresh water. Sadly, pollution makes much of the limited water unusable. It's estimated that 70% of China's surface water is unsafe for human consumption, and that the water is in half the country's major rivers is so contaminated that it's unsuited for any use, even agriculture. The situation in Shaanxi province exemplifies the problems of water pollution in China. An industrial powerhouse in the north-central part of the country, Shaanxi has about one-third of China's known coal resources and currently produces about two-thirds of the country's energy. In addition to power plants, major industries include steel mills, tar factories, and chemical plants. Water quality issues are also severe in India. Lack of wastewater treatment means that human waste is dumped directly into open ditches that flow to rivers. Human bodies are burned, and partially burned remains are thrown into rivers, along with dead animals and industrial effluents that make for extremely poor water quality. Countries put effort into managing and treating human wastes for multiple reasons. Chief among them is human health. Human waste contains more than 500 pathogenic bacteria, viruses, and parasites that can easily travel from humans and animals into waterways. Human and animal wastes, rich in nitrogen and phosphates, can also cause eutrophication. As we have noted, many poor countries have little, if any, wastewater treatment systems, and in some poor countries people urinate and defecate directly outside into the water or onto the soil. When human population densities are low, limited treatment of human wastes is acceptable because natural processes will break down the waste quickly. However, in cities with large numbers of people and limited room for bacterial action, this is unworkable. In some countries, notably Asia, night soil, which can be both human and animal waste, is spread on agricultural fields as fertilizer. This practice can be dangerous because there is limited, if any, treatment provided, and viruses and bacteria can contaminate crops. Outhouses, which were common in the United States in the past, were the standard method of waste disposal. This was also a less than ideal practice because deep outhouse holes could contaminate drinking water wells, which were often in close proximity to outhouses. Outhouses were eventually replaced with septic systems. In a septic system, waste is sent to a septic tank where solids and liquids are separated. The liquid portion of the waste is then sent to a drain field where the wastewater is treated by aeration and excess nutrients are removed through bacterial action. Solids, which remain in the septic tank, are pumped out and taken to a municipal treatment plant. Municipal sewage treatment involves multiple levels of treatment. These include primary treatment, which involves separating large solids from the waste stream and settling tanks to remove sludge. Secondary treatment uses aerobic bacteria to break down organic compounds in the wastewater. The final treatment level is tertiary treatment. Tertiary treatment is often optional and is not performed at all treatment facilities. Tertiary treatment is used to remove dissolved metals and nutrients, often using natural or constructed wetland systems. Let's take a little closer look at a municipal treatment plant. In this figure, we see a diagram of a municipal sewage treatment facility. Typical facilities complete primary and secondary treatment of wastewater. Looking at the diagram, we see that sewage is carried into the treatment plant via underground piping. Primary treatment involves screening, which removes large objects like diapers or wipes, etc., and placing the wastewater into tanks to separate the solids from the liquids. Solids are termed sludge. Water from the separation tank is then pumped into containers. In secondary treatment, the water is aerated to encourage bacteria to break down the dissolved organic materials. This water is then placed into a settlement tank, and here, more sludge that is formed at the bottom of the settling tank is removed. Again, the sludge is scraped and collected for treatment. The water at this stage is almost free from harmful substances and chemicals. The water is allowed to flow over a wall where it's filtered through a bed of sand to remove any additional particles. In this photograph, we see an image of a sewage treatment aeration tank, which is the secondary treatment portion of the process. Here, aerobic bacteria digest dissolved organic materials in high-pressure aeration tanks. Although wastewater is usually free of pathogens and organic material after secondary treatment, it still contains high levels of metals and inorganic nutrients. If discharged into surface waters, these nutrients can stimulate algal blooms and eutrophication. Allowing effluent to flow through a wetland or lagoon can remove nitrates and phosphates. Alternatively, chemicals often are used to bind and precipitate nutrients. Sewage sludge can be a valuable fertilizer, but it can be unsafe if it contains metals and toxic chemicals. Some cities spread sludge on farms and forest lands, while others convert it to methane or natural gas. Many cities, however, incinerate or landfill sludge, both expensive options. In many U.S. cities, sanitary sewers are connected to storm sewers, like the ones that drain water off of the street after it rains. However, heavy storms can overload the system, causing bypass dumping of raw sewage and toxic runoff directly into surface water. Combined sewer systems are not now commonly encouraged in the United States. Clean Water Act was ambitious, popular, and has been largely successful. Passage of the U.S. Clean Water Act in 1972 was a bold bipartisan step that made clean water a national priority. Along with the Endangered Species Act and the Clean Air Act, this is one of the most significant and effective pieces of environmental legislation ever passed by the U.S. Congress. It's also an immense and complex law with more than 500 sections regulating everything from urban runoff, industrial discharges, and municipal sewage treatment to land use practices and wetland drainage. The ambitious goal of the Clean Water Act was to return all United States surface waters to, quote, fishable and swimmable, quote unquote, conditions. For point sources, the Act requires discharge permits and uses use of best of practical technology, or BPT. For toxic substances, the Act sets national goals of best available economically achievable technology, or BAT, and zero discharge goals for 126 priority toxic pollutants. These regulations have had a positive effect on water quality. Although surface water is not yet swimmable or fishable everywhere in the United States, its quality has significantly improved on average over the last 25 years. Perhaps the most important result of the Act has been an investment of over $54 billion in federal funds and more than $128 billion in state and local funds for the construction of municipal sewage treatment facilities. One of the most successful regulatory programs of the Clean Water Act is the National Pollutant Discharge Elimination System. This permit system establishes limits on each facility and requires regular monitoring of effluent from point sources to ensure compliance. Facilities must maintain records which are reviewed by the EPA. This system applies to any facility that discharges any waste into the waters of the United States.